Sure. So, hi everyone. Good morning to people joining from US and other parts of the world, and good evening to the people who are joining from India or Asian countries. So, I'm Shadab, co-founder of Quantum Computing India, and we have Imam Darcy with us. He is from Australia and is having lots of achievements. Like he has a master's degree in e-commerce from Murdoch University, and he has won prestigious achievement prize as a student during those days. And after that, he went to La Trobe University in e-marketing and advanced e-commerce. And like he has also successfully completed 4 university certificates on quantum physics, quantum computing, and he has a good hold on this subject and being delivering talks and lectures and doing the research in this field from quite long. So I have attended 2 talks by Darcy, and it was a pleasure to attend those talks, and it's good to see him again live talking about today's topic. So I mean today he's going to talk about quantum contextuality and Peres-Mermin magic square. So before handing over the session to him, I will just quickly talk about Washington Quantum Computing Meetup Group. So let me see if I can share my screen. Yeah. So this week we have talk with Imam Darcy and on this topic. Next week also we have few of the upcoming sessions, and these are also very interesting. And if you have interest in any of the sessions, if you want to be the speaker or the moderator, please get in touch with Helen or Debso. So they will be the right point of contact for it. So few of the interesting sessions, if you see, we have next week on efficient computational methods for quantum molecular dynamics. Then D1 properties and applications of entanglement of indistinguishable particles. Then also there is one coming with Pavel and Javier on supervised learning using QML in real world cases. That's going to happen on October 22nd. So if anyone of you have interest in machine learning and quantum machine learning, then I mean definitely you should go for these sessions. And many more lined up for the month of October and November. If you have not joined up the meetup group, or if you want to stay up to date with what webinars or sessions we are going to organize, please feel free to join the Washington Quantum Meetup group on Meetup, and you can connect with Helen Mai as well on LinkedIn, so you will get the updates. And these are few of our sponsors: Quantum AI Foundation, Association Quantum, Orion X, Artisan, Q Poland, Cambridge Quantum, and Quantum Computing India. So that's it from my side. Stage is over to you, Darcy.
I'm looking forward for the... Okay, thank you very much. Yeah, if you stop sharing, and I'll start sharing. Now, can everybody see the screen?
Yes, screen is clear. Eamon, if you could mute everybody else, that'd be great. Thank you.
Oh, yeah, can I do that? Or Helen, can you mute everybody?
Yes, everybody's mute.
Everybody's muted. Okay, so am I ready to start?
Yes.
Wonderful. Okay, well, first of all, a big thank you for you all attending here. I hope you're going to enjoy this lecture presentation as much as Anna and I have enjoyed putting it together, because this is what it's all about. This is what quantum physics is all about. It really is. Today we're going to present on quantum contextuality and the Peres-Mermin magic square, which basically proved the quantum contextuality, if you like. And my co-presenter is Anna Naden, who is doing amazing work. She's actually coding this, the Peres-Mermin, which is, well, the Peres-Mermin's been around since 1990. Contextuality's been around since 1966, 67. And Anna is actually writing code to run it on a quantum computer, and she emails me constantly, daily, about all the updates. But tonight, this evening, I'm going to go through a few things and then play a 10-minute video that Anna presented to her meetup group only about a week or so ago, maybe a couple of weeks ago. And then Anna will come on and give you all the update of how the coding is going. It's more a problem with noise and pure qubits than anything else, but I'll leave all that to Anna because that's certainly what she does best, and she's just wonderful. But let me now tell you what quantum contextuality is and the Peres-Mermin. Before I do that, please indulge me for a couple of quotations. I mean, quantum physics is famous for quotations, and most of you will have heard these too, I'm sure. But I love starting off with this because I don't think we should ever forget the magic, the mystery of quantum physics. And I love this statement by Heisenberg, Werner Heisenberg. He was saying, it was about 3 o'clock at night when the final result of the calculation, which gave birth to quantum mechanics, lay before me. At first, I was deeply shaken. I was so excited that I could not think of sleep. So I left the house and awaited the sunrise on top of a rock. I just think that's beautiful. And we're talking nature. Let's always remember the quantum world is nature. The real world is the quantum world. The world we live in, touch, feel, see, inhabit is not the fundamental empirical real world. Now, of course, you've got to throw in a Feynman. And I love this quote, but I'm actually twisting this quote around. Let me just say, it doesn't matter how beautiful your theory is, doesn't matter how smart you are, if it doesn't agree with experiments, it's wrong. And, you know, we would all agree with that. We would all agree with that in the classical world. I put it to you that in the quantum world, and in fact, what we're going to talk about tonight, is that the reality, what do you do when the experiment works when in reality it shouldn't? And what I'm going to show you is a game, the Peres-Mermin magic square, that obviously you shouldn't win every time. You obviously can't, and I show you why not. Yet, with quantum entangled qubits, you will win every time for infinity, for an infinite number of games. Now, that is amazing. I may add that I do a lot of teaching, as Shadab very kindly mentioned, and I teach here at the CSIRO. I don't know whether you know what that is, it's an Australian thing. But I now start teaching high school children. I start off now with the Peres-Mermin because it gets them excited. It's unbelievable. And it's unbelievable that Anna's going to code it. So let's get into it because it's so fantastic. Right, the table of contents. By the way, I hope you like my graphics. I've done them all myself. They're all AI generated. I'm into AI art generation at the moment. Okay, I'm going to talk about quantum contextuality, which is essentially the Kochen-Specker Theorem in 1967, also known as the Bell-Kochen-Specker Theorem, because Bell was a part of it. John Bell from Bell's inequality fame, and it's all wrapped up with each other. The CHSH game, which some of you will know about, which Anna's coded as well, I might add, and the Peres-Mermin and all these things. Then I'm going to talk about the practical uses of the quantum solution to the Peres-Mermin. So, and I can only tell you about the uses we know about, which is basically random number generation. But I suspect the military are doing some amazing stuff with this contextuality and the magic of the Peres-Mermin, because it is succeeding to do something that is, from all we've known in 2,000 years of mankind and womankind's progression, everything we've learned in the last 2,000 years goes out the window with this game. Really interesting. And then the wonderful Anna Naden will give a short 10-minute video. I've already taped it, so I'll just play her video, and then she'll come on live. Hopefully, there's a couple of technical issues, but hopefully they'll be solved. And she's talk about the coding on the Peres-Mermin. And then we'll have questions and hopefully some answers. Let's go. More AI generated art. Oh dear. Quantum contextuality. The Kochen-Specker Theorem, 1967, often referred to as the Bell-Kochen-Specker Theorem, states that, now, given a premise of non-contextuality, certain sets of quantum mechanical observables cannot consistently be assigned definite values. Now, don't worry if you don't understand at the moment, because I'm going to refer back to this. But what it's saying is non-contextuality is where the object has its own clearly defined properties and is a thing. But contextuality, which I will explain in a second, is where it depends on how you measure it and what you measure it with, determines on what that actual thing is. Nothing in the classical Newtonian works that way, nothing. So, it's all down to these observables that if you say they have a defined value, like Einstein does, then it shouldn't be able to do what it does. The Peres-Mermin magic square should not work cannot work if a quantum particle has clearly defined properties. Now, it's a no-go theorem, rather like the CHSH and many like that, which basically means reality, this defies reality. And it certainly does. The good thing about the Peres-Mermin, which came in 1990, about 25 years after contextuality, the Kochen-Specker theorem, the Bell-Kochen-Specker theorem, was very involved. It used over 100 observables, very complex maths, and nobody could understand it except for those three people. So the Peres-Mermin, that's David Mermin, who's written many, I'm sure you all know, quantum textbooks, and Asher Perez, they reduced it to only 9 observables, and they actually, and by the way, their paper, they both wrote a paper on it, and it's on archive. The Perez paper was 1.5 pages, and the David Mermin paper was 3.5 pages. They like to make things simple, and thanks to them, we can do a game now which will show the incredible, mysterious quantum forces are real. But they made it very easy to follow. Now, okay, I'm going to give you a classical analogy of quantum contextuality. Let's say a quantum particle is a car. Now, in the I nearly said the real world. In the Newtonian world, the classical world, the car is an object and it's objective. It doesn't matter how you look at it or which way you look at it or how many of you look at it or what you measure, it's always the same thing. It's either a BMW or a Porsche in this case. But in the quantum world, quantum contextuality says a car, in this analogy, a car is a BMW if we measure for example, the fuel injection and the aerodynamics, then that quantum particle will be a BMW. However, if we measured the suspension and the power steering, that car would be a Porsche. So how can that be? How can it be that depending on other measurements gives you the fundamental properties of an object? It's really, really amazing, but we know it's true because the Peres-Mermin works. Now, let's go back now to a quantum contextuality. So the same thing applies. The identity of the quantum particle depends on the context. The measurement outcome will be different if we measure it using different properties. So if we measure using for example, the angular momentum and the energy, notice they have to be commuting observables. We'll talk about that in a second. It will be one thing, but if we measure it with the orbital momentum and the energy, it will be different, which is very handy for this game, as you'll find out soon. But that's what quantum contextuality is saying. Now, in fact, quantum contextuality, quantum entanglement, superposition, all of quantum physics comes down to that top question. And you can see the standard of people who have conflicting views. Does a subatomic particle have well-defined properties? Yes or no? Einstein said it did. Now, he said some of these properties we can't assess yet. They're hidden. We all remember the EPR paradox. Einstein, Podolsky, and Rosen's paper, the EPR paper, that challenged quantum entanglement. But basically it still came down to checking that, Einstein was saying, no, a quantum particle has well-defined properties. Some of them may be hidden from us that we can't access, but they're real. So did Schrödinger and de Broglie. You may know him for the pilot wave interpretation of quantum mechanics, where he says position is always a definite value. And on the other hand, Heisenberg, Pauli, Wolfgang Pauli, Born and Bohr said, no, it's not. It's in a strange position. It's in a quantum particle is in this strange reality that we're not used to, but it is a reality. Now, we all know Bell's inequality, or I have to assume that we do, because I won't be going into it deeply now. We've all done a presentation on it. But the big question is, when did these properties come into existence? This is what Bell's inequality uncovered. Because Einstein said, when the particle's created, it has all its values. And Bell said, no, it doesn't. It's in a weird reality we don't quite understand until it's measured, and then the properties come into existence. Now, let me tell you what this is like. Hello, everybody. Now look at this graphic design on the right. I spent hours on this. Now listen, my hair is blue. It's just that whenever anybody looks at me, it instantly turns gray. Prove me wrong or prove me right. Now, this is the problem that quantum physics had. After from 1925, I think can't remember when the EPR was. I think the EPR was either 25 or 35. But irrespective of that, there was no way of proving it. Wolfgang Pauli, of all people, he said, well, it's really interesting, but we'll never be able to prove whether, now, I mean, my hair being blue is obviously a bit of an analogy, but we'll never be able to tell if a particle was in superposition, because every time we look at it, it's become a particle. And you know what I mean, measure it, observe it, there's no right word. We need to create a quantum lexicon. I'm sure somebody is in the process of doing it. Anna can do it. She's got a lot of spare time on her hands. Joking, Anna. But how could you prove me wrong? Think about it. You can't. My hair's blue. It's just that when you look at me, it's grey. But Bell did mathematically prove, and that was the beauty of it, that the particles, the properties come into existence. He didn't prove particularly superposition existed. He was saying the particles come into existence when they're observed, measured, or whatever that word is. Wow. But let's get on to the Peres-Mermin. How am I doing for time? 5 to 9, that's fine. The Peres-Mermin magic square, you're going to enjoy this, everybody. Now, what's it used for, by the way? It's used by NIST. So this is a practical use of it that I mentioned earlier. You know, the National Institute of Standards and Technology, and what they have is the NIST public randomness beacon, and they use the likes of the to generate certified random numbers, and they use the CHSH paradox and the Peres-Mermin, which aren't totally different. They're both games or paradoxes where entangled qubits give you a better result than you would expect. And talking about that, what is the Peres-Mermin? So it's a Bayesian game with imperfect asymmetric information. So what does that mean? It means it's a game based on Bayesian probability, or has got a bit of that involved, with imperfect. So the information you have is not enough to win the game every time. Asymmetric means I know something you don't know, and you know something I don't know, but we can't communicate them. Now, the Peres-Mermin, they used it, I think they coined the phrase, please correct me if I'm wrong, for quantum pseudo-telepathy, which of course is a bit of woo-woo, but gets people interested. I often say, I have presented on a number of occasions to the spiritual community in Perth and WA, and I always say, look, instead of, you know, talking about clairvoyance and telepathy, which have never been proven experimentally, scientifically, you know, why, and I hope I'm not offending anybody by saying that, and if you could prove me wrong, I would be the most interested to see your proof. Quantum pseudo-telepathy is actually nothing to do with communicating over vast distances, but it's actually mitigating the need for that. It is using entanglement. It is actually a form of communication that means you don't have to communicate to win the Peres-Mermin, for example. And this is so exciting because the Peres-Mermin game, which I'm sure the military are using in some way, could be played, you know, and they could be 100 million miles away from each other, but it doesn't matter because of quantum entangled qubits. And Anna will talk a little bit more about that. So it's all down to entanglement and contextuality. But let's get on to the game. Now, the US had an initiative at the beginning of this year to, can you learn quantum computing by playing quantum games? And they exhibited on Quantum Day, which I think was in May. I can't remember when it was. But they have done these great websites, great games, quantum chess. There's literally about 30 odd games, and they are worth looking at. And one of the games is actually the Peres-Mermin game, which is this one here. They call it zeros and ones. So I'll follow the nomenclature for the moment because the concept is the same. Anna will be talking plus ones and minus ones because it makes the mathematics cleaner. But it sort of doesn't really matter. So look how simple this is. It's a tic-tac-toe board, I think you call it. We call it a noughts and crosses board, and you've got tokens that can be 1 or 0. That's simple, not complex at all. Now, you have two teams, a blue team and a red team, and they're actually working together. They need to work together to win the game. And there's also a referee who just checks that the rules are being adhered to, and he does a random distribution, which I'll tell you about in a second. But I think somebody needs to mute. Okay, so the blue team can, it can be one person or a dozen. The blue team fills out the rows, and it needs an even number of ones. On the other hand, the red team can only fill out the columns, and it needs an odd number of ones. What could be easier? Now, they both win as a team collaboratively when the overlapping square, and there will always be one in a 3x3 matrix, when you've got 3 digits in a row, 3 digits in a column, one of them will be the overlapping square, and they win the game when both are zeros or both are ones, when the overlapping square is the same. Now, when you think about it, each of them only have 4 combinations of 3 digits that they can use. The blue, let's remember, can only do the rows, and let's remember it has to be an even number of ones. So the top one, 0, 0, 0, is counted as even. The second one, 0, 1, 1, even. It's up to 2. 1, 0, 1 is 2. And 1, 1, 0 is 2, which is an even number. So they are the only options that the blue team have. And the red team, they are doing the columns, remember, and they have to be odd. And they only have 4 possible combinations that obey the rules. I'm sure everybody can see that. Now, here's the important thing. Before the referee starts the game, the blue and red team, and by the way, play this amongst yourselves with your family and friends, you can decide upon a strategy, whatever classical strategy you want. You know, you might say, look, I'll do 1, 1, 1, you do 1, 1, 0, and that's given us a greater chance that the ones will overlap, anything, something like that. However, as soon as the referee starts the game, please excuse me. As soon as the referee starts the game, you cannot communicate. Blue does not know what row, what column the red digits have gone in, and red doesn't know what digits the blue team has gone into. Now, the referee randomly chooses which row it's going to go in. So let's say it says to the blue team, give me your row, and they may say 1, 1, 0. And then the referee throws a dice or has a random number generator from 1 to 3. And if it's a 1, the referee will put those digits in the top row. If it's a 2, middle. If it's a 3, in the bottom. And likewise with the columns, the referee will roll the dice again. or the number generator again, and that will determine whether the 3 digits provided by the red team go in the left, center, or right. And look, it's a lot of fun to play. But spoiler alert, and you know, you guys are clever, you'll get onto this straight away. There's always once where placing a 0 or a 1 will violate one of the game rules. There's always one. You can try it out yourself. If you look on the right, you can see the bottom right-hand corner. If I put a 0, then the blue team, the row will be odd, and that's not allowed. If I put a 1, then the red column will be even, and that's not allowed. You can only win 8/9 of the time. And I'm sure you agree on that. So to win every game, it's just not impossible. You can win one. You've got 8/9 chance of winning the first game. And you can see the big formula on the right. N is the number of games. So the number of rounds or games that you play is the exponent of 8/9. So if you play just 4 rounds, the chance of you winning is a little over 50%. And I'm sure you're all okay with that. When we get to just 24 rounds, then your chances of winning are less than 1 in 1,000. It's amazing. Look at that. Just with playing 24 rounds, it's less than 1 in 1,000. Now, as you know, I'm the founder of Quechua, and I had a big party night with all of my friends, my quantum friends from around the world. There was Vic from Quantum Malaysia, Lorraine from Quantum, she's the president of Quantum Africa. And then I had Australia, England, and India. And we all played the games. And these were people who their audience had never heard of the Peres-Mermin. They just played the 1s and 0s game. And I can tell you that immediately we started, after 4 games, we were, 2 of the teams were excluded. So I think this was a bit of fun. We really, a little bit of theatre. I don't think we needed it to prove that you cannot win. So when I told them, and when they told their other team members that using a quantum strategy, we could win every time, no matter how many times you played, millions of times. Imagine what the astronomics of that are. Unbelievable. But when you play with entangled qubits, you'll win every time. Now, let's get back to, remember I showed you the cars, the BMW and the Porsche and the orbital momentum and the angular momentum. This is how the Peres-Mermin proves contextuality, because the identity of the quantum particle depends on the other observables, as we've agreed. So if you're measuring it in a row, it will actually give, for the question mark in the bottom right-hand corner, it will give a different answer if you're measuring it as a column. Nothing in the Newtonian world works like that. Now, there is the formula which Anna's assiduously worked on for the Peres-Mermin. Now, these are 9 observables that Asher Perez and David Mermin put together, and I is the identity matrix, so that's a 2 by 2 matrix, and the X, Y, and Z are the Pauli matrices, and they are 2-dimension 2x2 matrices as well. So when you, and then of course they're just matrices, so we can get the tensor product of the two of them, which will give us a 4x4 column matrix, for each square, each observable. And Anna's done that in her coding. Now, the first thing to note is that the observables in each row and each column commute with each other. So taking one row at a time, the three observables are commuting. That means you can measure them all at the same time. Whereas Heisenberg, as we all know, told us you can't measure momentum and location, so they're non-commuting. But the three measurements in the row, are the three observables in each row do commute. And also in the column, they all commute. But they may not all commute with each other in the entire matrix. But when it comes to each row and each column, they all commute. And as I say, each square is a tensor product of a 2x2 matrices, and the tensor product gives you a 4x4. And each square has an eigenvalue of plus or minus 1. And the other thing is, all three observables in a given row, when multiplied together, will give the unit operator, i.e. they'll give 1. You can see in the rows, so if you look in the far right, you'll see the top row gives 1, the second row gives 1, the middle row gives 1, and the bottom row gives a 1 when the three observables are multiplied. This is also true for the columns, with the exception of the third column, where they actually give us the minus unit operator. And this is the way Peres-Mermin set it up. I'm now going to play a video that Anna from her meeting.
You've got to enable the sound when you share the video.
It is enabled.
No.
Sorry, you can't hear it.
When you share it, there's a checkbox.
Yeah, I did. I know I did check those boxes. I'll just stop sharing. Sorry, everybody. Apparently, you couldn't hear the audio. I'll share again. I'm aware you have to check those boxes, and see that they're checked here. So let me try again.
They can win the game every time. So my Australian partner, Amon, whom many of you.
Can you hear that?
Yeah, we can hear it now, I think.
Oh, fantastic. Okay.
I completed a quantum program. Many of you have attended my meetup events on the Magic Squares game, the Peres-Mermin Squares game. And many times I've shown by various ways that quantum computers, if Alice and Bob, the two players, have quantum computers, they can win the game every time. So my Australian partner, Amon, whom many of you know, challenged me to get this running on IBM's quantum computer. The language is called Qiskit. And so I did it. I got a program. I'll show it to you, and I'll show you the results. So for those of you who maybe missed the presentation or have forgotten, The rules of the game are there are two players, Alice and Bob, and either they win collectively or they lose. And the referee tells Alice which row to play on, the first one, the second one, and the third one. And she responds by putting down a pattern of ones and negative ones. Sometimes it's presented in terms of ones and zeros, but the math works out a little cleaner with ones and minus ones. So she's required to have an even number of negative ones. And in this case, there are no negative ones, so that's 0, and 0 is an even number. The referee tells Bob to play in the second column, and Bob's rule is different. He's required to put down an odd number of negative ones. So in this example, he has 1 negative 1. That's an odd number. And in order for the players to win, there's one square that Alice and Bob have in common. And in order for them to win, they have to both put down the same thing in that square, either both put down 1 or both put down -1. Are there any questions about the rules of the game? It's fairly easy to show that there's no strategy. Alice and Bob aren't allowed to communicate. Bob doesn't know what Alice did. And so the best they can do is agree in advance on what they're gonna do, depending on what the referee says. And it's fairly easy to show that there's no strategy that wins 100% of the time. They can only win 8 times out of 9. However, if Alice and Bob have a quantum computer, each of them has a quantum computer, and they meet before the game starts and entangle the qubits on their machines, and then they separate. They could be on different galaxies. They're not communicating, but they have these entangled quantum computers. And when it's Alice's turn, she simply asks her computer what move to make, and the computer gives her a sequence, 1, -1, 1, for example. My quantum program generates Alice's move and Bob's move. Bob can't see Alice's qubits, and Alice can't see Bob's qubits. So when you run a program on IBM's quantum computer, it's a statistical process. It's a probabilistic process. And you get back these counts. We had 7 quantum bits. We measure them all. Well, we don't measure this last one, so it's 0 all the way. But we measured the other 6. And these first 3 qubits right here are Alice's move. And the way it's set up is if you get a measurement of 1, that means Alice played -1 in the first square. If the measurement is 0, it means she got +1. I'm sorry, if the count is 1, it means she played a +1. And if the count is 0, it's a -1. So here she had 2 -1s, which is what she has to do by the rules of the game. These are Bob's qubits, Bob's counts. And the requirement is that Alice's, in the overlapping square, which is here and here, they have to agree, and they do agree. So basically, they won the game. And for each of these results, each of these bars in the bar chart represents a different game outcome. But if you check them carefully, you'll see that they win in every case. Well, then I was very excited to run it on a live quantum computer, and I did. And this is what I got. Total trash. So I'm trying to get access to a better quantum computer that hopefully will give the right results. Now I'm going to demonstrate the simulation.
On IBM, how many times did you run the experiment for each possible outcome?
I ran it up to 16,000 times. I was very disappointed. Now I'm going to demonstrate that in the simulation mode, they win. So here's the results again. Now, if I close that, oh, I'm not sharing the right thing. Well, it is probabilistic. There are like 6 different ways they can win the game. And it's probabilistic which of those winning outcomes you get. But what is deterministic, what is not random, is whether they win or not. They win every time if there's no noise in the computer. So now you should see a 3x3 grid titled row 0, column 1, with -1s and 1s. So this shows that they won. Here's Alice's move, 2 -1s, an even number. Here's Bob's column, an odd number of -1s. But you get a series of these outcomes, all of them winning, but with different winning moves. So here, we've got these annoying pop-ups again. This statement right here, I don't know, can you see my mouse cursor?
Yes.
Q equals quantum register 4. That says there are 4 qubits. Alice gets the first 2 qubits and Bob gets the second 2. But I wanted to experiment. See, I've heard that on IBM's computer, not all physical qubits are created equally. They have different operating characteristics, different interconnections between them. So I created this permutation where I control which physical qubits Alice uses and which ones Bob uses. And by changing this permute function, see here, I've got 0, 2, 1, 3. That says Alice gets the 0th physical qubit and the second qubit. Bob gets the first and third. Initially, I ran 0, 1, 2, 3. I thought maybe I'd get better results if I used different qubits, but actually the results were worse or just as bad. One of my goals is to score the quantum computer and give a measure of, did it win any games at all, more than random chance? That's something I'll be working on soon. But here's Alice's moves. She has 3 moves, so the counter I runs from 0 to 2. She performs a measurement, well, her computer performs a measurement just on her qubits. See, it says Alice. It's Alice, that's the first 2 qubits. Now we've got to undo the transformation so that we can get back to the correct quantum state. And this is probably the reason why we're getting random results, is we're doing 12 unitary transformations, and each one is noisy, so you get a lot of noise. Here's Bob's move, 3 steps, 3 squares. It's basically the same strategy as Alice. Anyway, that's where I'm at tonight.
So your for loop, your for I loop, that represents the information given to Alice by the referee?
No, that's classical information. It's represented in the variable row and the variable column. What I stepping through 3 values represents the 3 squares that Alice's computer has to tell her what to do with. I hope you enjoyed it. It was fun presenting it. You've been a great bunch.
Okay, so let's have a current update from Anna. That was a couple of weeks back with respect to running the Peres-Mermin on a quantum computer. So I'll stop sharing. Anna, if you could possibly, oh, there you are. Can you take over?
Sure. Um, okay, so I just want to review the way they play the game. Alice and Bob meet before the game, they entangle their computers, then they separate so they can't communicate. The referee tells Alice what row to fill. She asks her computer what move to make. The referee tells Bob what column to fill. Bob asks his computer what move to make, and they win every time. So I simulated this as you've heard. I have one quantum computer rather than one for Alice and one for Bob. But the way it's programmed, Alice's part of the computation doesn't see Bob's qubits and Bob's part doesn't see Alice's qubits. So it's as if they weren't communicating. I run it thousands of times. You get a lot of game outcomes, but everyone is a win. So here's a summary of the outcome. It's based on unitary transformations, which are like rotations in the quantum space. Random guessing would result in a failure 87.5% of the time, 7 times out of 8. Either one player makes an illegal move, or they both make legal moves, but they don't agree on the overlapping squares, so they lose the game. When you run it in simulation mode, they never fail. The moves are always legal and the players always win. On a live computer, the failure rate depends on a threshold, which I'll explain in a moment. The most common failure is that Bob plays differently from Alice on the common square. That's what usually goes wrong. So there are 2 ways to calculate the win probability. One is to set a threshold, which is what I've done here. And I just keep the most probable outcomes. Now, just this morning, I realized the other way is to take the probability of each outcome, which is basically the height of the bar. And if they win, I add that to their win probability. It gives you a similar number, but slightly lower. So here's the results in simulation mode. And here's the results in live mode. Now, I thought this was pretty bad, but I discovered something, and I'll share it with you now. what I've done here is I've just computed Alice's move only, not Bob's. And as you can see, Alice got an even number of -1s. This is with the real live quantum computer, the noisy computer. Here's another outcome. Again, 2 -1s as she's supposed to. And if you run through all the outcomes, Alice plays a legal move every time. So the quantum computer and Bob's moves are often legal too. Where usually they fail is that Alice's move is inconsistent with Bob's move. They don't play the same value on the overlapping square. And what that says is that the entanglement between the two pairs of qubits is not perfect due to noise. Are there any questions or comments?
So does this relate to the decoherence time of the qubits? Like there's a limit as to how long they'll remain entangled. So the process of doing the transformation and undoing it twice, the first for Alice and then the second time for Bob, is that too long for the qubits to remain fully entangled?
Probably. I mean, every step, every unitary transformation is a number of individual steps in the computation. They all take time, like a millisecond or something. And by the time we get to the end of the computation, the information, the quantumness is lost. And one thing you can see in the results is that usually Bob has more errors than Alice. So I think your comment is right on. I think that's probably what's going on.
And on a regular CPU, I would consider taking those two loops and interleaving the instructions so that you're processing the steps both you're trying to advance both of them at the same time. I'm not clear because I don't quite see what each of the unitary steps are. I don't see what the quantum circuit is that you're trying to simulate or trying to run. Is it possible to do both measurements in parallel so that you essentially have the same error level for both Alice and for Bob? Would that improve the correlation between the two, perhaps?
I didn't think I could do that. And the reason is because each measurement depends on the quantum state that resulted from the previous measurement. It's a linear process. So that Bob doesn't have the right state until after Alice has done her measurements. So
even though those are operating on a separate set of qubits, right? Because you have 3 qubits that are dedicated for Alice and 3 qubits that are dedicated for Bob, right?
But they're entangled with one another. Bob's qubits are entangled with Alice's qubits. So when Alice performs a measurement, it modifies Bob's qubits.
Right, and then you're trying to undo that by reversing the operation because it's each quantum gate is reversible.
Yes, but I don't reverse the measurement. Measurements are irreversible.
Right, that's when it's collapsed and you get a definite state for the qubits that you're trying to test.
Yes. So
is it possible? Is it possible to run it on? No, you can't entangle 2 separate quantum computers yet, can you? and the Qiskit cloud and the IBM Q cloud?
No, I don't think you can do it.
It'd be an interesting experiment though, wouldn't it?
It would be an interesting experiment. If you could run a quantum computer and save the quantum state and pass it to the next quantum computer, that would do what you're asking for. And you can do that with a simulator. You can run the simulator and it'll give you a set of 16 numbers for the quantum state. And but then you'd have to initialize the other computer to that quantum state, and that would be difficult. But
I don't think
real
that's actually
computers-
allowed, isn't it? Right? Because we don't yet have quantum memory. That's the whole problem, is that you're trying to build the quantum memory by undoing all of the steps.
Quantum memory is very limited. You can capture a photon and play it back like 20 milliseconds later and have it be in this state that it went in. But for any longer period, you can't. And if you have to transmit it over a distance, like across the room, again, we don't have it.
Right. So is there a solution? Is this doable? I'm fascinated by the prospect of actually being able to run this on a real machine, but and I suppose if you actually built custom hardware, you could consider doing that, where you could actually do the photonic entanglement across a distance. Have two quantum computers separated by a fiber optic link and use that to share the original entanglement, right? Maybe that's doable.
I think it is doable. You could build a custom processor. It wouldn't be programmable, but it would perform all the operations. It would be a one-trick pony. It would only play the Peres-Mermin game. You couldn't program it, but you could do it with photons and Bell state analyzers, beam splitters, phase shifters, things like that.
But probably not on the IBM Q world, since they don't have that type of communications established between the machines.
No, they don't. They have waveguides, microwave waveguides going from one qubit to another one, but not from one machine to another one. It's in a big cabinet with a refrigerator around it. A dilution refrigerator, $1 million refrigerator.
They're impressive machines, at least the pictures are. But yes, but the whole point is, how could you get one there are ways to do and share entanglement across large distances.
Yes.
However, it requires all that custom hardware, as you mentioned.
I think it's only been done with photons.
I do believe so. I'm not an expert, but I've been trying to read up a lot on this, and it does seem that that's the only way to do it at a distance. The photons like to travel, right? Because they don't stop, and or at least it's hard to slow them down. And so that seems to be the most likely way to do this, where you could actually build a machine to do the magic square test.
Yep. So here's how I wrote the algorithm. I started off with the observables that Amon showed you. I converted them to unitary matrices by finding the eigenvectors. These unitary matrices are basically the measurement operators. They modify the quantum state and perform the measurement. I pass them the gates, which are provided by IBM. I perform measurements. I extracted counts, and then I converted the counts to a game outcome. So here are the observables. This is the magic square. These are the Pauli spin matrices, X, Y, and Z. This is the same X as here, the same Y, the same Z. So I've printed out the actual numbers for one square. It's a 4 by 4 matrix. This is the square root of 2, the square root of 1/2. Then I converted them to unitary matrices by computing the eigenvectors. And if you look closely, this is orthogonal to this. If you take the dot product, you get 0, as it must be for a unitary matrix. This is from IBM's quantum experience. You could go online and construct a quantum circuit. You might even be able to do the Peres-Mermin circuit, but this is a drag and drop operation. Off to the left, where you can't see it, is a palette, a list of gates, and you just drag the gate over here. This is qubit 0, qubit 1, qubit 2, and qubit 3. These are the measurements. So this is like a graphic representation of what my quantum program does. This gives us the counts. Each count is a possible game outcome. This is for the simulation. This is a game outcome. Even number of -1s in the row, an odd number in the column. So the quantum program was only about 50 lines, and I'll show it to you in a moment. The supporting code was another 200 lines of code. So this sets up the qubits. The way I have it set up, I control the number of qubits so I can have more than 4. You have classical registers, which are just bits, 7 bits. You create the circuit. This initialize function creates an entangled Bell state. This is basically what Alice and Bob do before the game starts. They entangle their qubits. That's what this function does. This is Alice's qubits. Now, I want to control what physical qubits Alice uses and what physical qubits Bob uses, because IBM provided a tool that'll tell you for a given circuit, for a given quantum program, which qubits will work best. And so I use this permutation to control that. I get the unitary matrix. I apply it as a quantum gate. Now, I've been experimenting with noise, where I inject noise into the simulation. I'm basically trying to find out what is the nature of the noise. Is it decoherence? Is it crosstalk between qubits? Or is it that the gates aren't doing what they're supposed to do, gate infidelity? Then a measurement. This unitary transformation is is to set up the measurement, because you're not measuring in the Z basis, the computational basis. You're not measuring with respect to 0 and 1. You're measuring with respect to superpositions. So that's what the unitary is for. Bob and Alice don't want the unitary, and so you have to reverse it after the measurement. So this is Alice's computer, which operates on her qubits. This is Bob's computer, which operates on his qubits. Now, the next project has to do this really, there's a new programming language. It's better than Qiskit. It's a high-level language. It has physics built right into it. It was developed by graduate students in Switzerland. There's no compiler for it, so you can't run it on a live computer. You can only run it in simulation mode. But some members of our community have begun work on a compiler. And we need volunteers because writing compilers is a big deal. So if you want to try your hand at coding a compiler for a quantum language, send me a text message or an email, anna@quantumwithanna.com. That's all I have. There's plenty of time for discussion if there's more comments.
Oh, wonderful, Anna. Thank you very much. And thank you, Ken, for the great question. Helen, are you still there?
Yes, I have a question.
Oh, right. Okay.
Do you have a compiler even though in simulation mode?
Pardon me?
You have a compiler even though you're in simulation mode?
No, I just, Qiskit, IBM's quantum library, Qiskit executes my script. I write the Python and then IBM executes it. Does that answer the question?
Oh, yes, thank you. And another question from Kino. What is the name of the Swiss Qiskit analog?
Silk, S-I-L-Q.
Hi, Anna,
I'm
can I
going to
ask
be
you a question?
presenting on that tonight. It's 7 p.m. Central Chicago time.
Is it today?
Today, yes.
Oh, good. Okay.
In about 10 hours.
Where will that presentation be? On Meetup, or how does one join that?
Meetup, go to Quantum Computing with Anna, and you'll see it.
So it's all about Slick?
What?
Is it all about Slick?
Silk, yeah.
Yeah, okay.
So I had a comment about this Silk compiler. The tools that they have an interpreter, and the interpreter only interprets for simulation purposes what a compiler would do would be to take the Silk language and emit either Qiskit or something below Qiskit so that it can be delivered to actual hardware.
Yep. And we're going to do that.
Yeah. And Anna, great presentation once again.
Thank you, Ron.
Hi, Anna. About your simulation, it seems to be perfect. Why do we need to move to a physical quantum computer if your simulator works?
Well, I wanted to run it on a real quantum computer. I mean, it would make a nice demonstration, and it taught us a great deal about the limitations of these quantum computers, that they're just far from perfect, and we wouldn't know how imperfect they were if we hadn't tried to run it on the real computer.
Can you talk about how you simulate? How is your simulator running?
Well, it's a Python script. I'll show you the script again.
I would add that the reason for running it on quantum hardware is that the simulation won't scale. If you decided you wanted to play this game on a 9x9 matrix, it starts getting to the point where you can't simulate it anymore.
Right. The amount of memory you need goes up as 2 to the power of the number of qubits. So you're limited in simulation to like 30 or 40 qubits.
Hi, Anna. Here's Kino. Is the Silk Python associated like Qiskit?
No, it's its own language.
Okay, thank you.
It has data types for classical data, data types for quantum data. It has functions that return quantum states or accept quantum states as input to the function. It's very advanced. It has physics built right into it, quantum physics. But this is the Qiskit.
I mean, the reason I asked is that it seems like the simulator solved the problem. And in real life, I could use a simulator to solve problems until the hardware catches up, right?
Yep. You could. But
Or your
problems that are
simulator is
really
biased towards yourself.
significantly hard take so many qubits that you can't simulate it. They take more than 40 qubits. Are there any other comments?
Yeah, I have a question. Here's Kino. Is the error rate around about 20% and it doesn't matter?
You can do better. The error rate with a quantum computer, with IBM's quantum computer, the error rate is like 70%. I've gotten it down to 50% by excluding the less probable outcomes. It's kind of a dodgy maneuver, but I've got it down to 50%.
Okay, because we used quantum computers and we evaluated at high performance computers, and it was so that we had an error rate of 20% at the IBMs in the outcome.
I would say that's pretty good. That's better than what I've been able to do.
So I'd like to go back on the original opening of the topic and then come back to Anna, if that's okay, because I think there are some fundamental understanding bit of thing. And again, this is purely as a matter of discussion. I'm learning here, and I'd like to challenge some of the assumptions. Likewise, I would like to learn from you guys in terms of what's happening here. So can we go back to Eamon's slide? And please feel free to jump in so that something that I'm saying does not make sense scientifically or mathematically. That would be great. Yeah. Can we go back to Eamon's slide, please? Eamon, if you can scroll on, please. So I think the first thing to understand is what is quantum? What does quantum, the word itself, comes from? And I think we started with the notion that you could have multiple properties, and when you measure one, the particle detected is different. Is that the context, Eamon? If you go ahead, please.
Yeah. Hi. Sorry. Can you read? I'm having a problem moving the. I don't know why that's. Great. Okay. So yes.
So
can you repeat the question, please? I'm so sorry.
So if you go back to the start of the thing, and also I wanted to discuss what does actually entanglement means, because I think to me it comes across that there are certain. So here we are. If you go, okay, the one after that, please. The slide after that. Yeah, keep going. Okay, and then keep going, please. And here, so we started with the notion here that the identity of the car, which could be a particle, whichever depends on the context. But I think if we really look at it, I think this is, to me, and this is why I was a bit lost in the presentation. I'm sorry. Yeah, I think that one of the important facets is that subatomic particle and quantum particles, they're completely different things, and yet they're connected. So what I mean by this is you have an electron, which is a subatomic particle, but you could utilize its quantum properties as a quantum particle, and therefore you could call it quantum particle. What does quantum means comes from the word quanta, which means a packet of energy or whatever. And if you look at, for example, spin, which is an intrinsic form of angular momentum carried by elementary particles, with the most important part here is that when you're measuring, when you look at the property of certain things, right? You can only measure one property from a pair of conjugates that can be known with certainty. And that is essentially what the principle of Heisenberg's uncertainty principle is. Plus, at the same time, it is also part of the no cloning theorem, right? So, this BMW and Porsche, by the way, just to take a aside from this, is that you do have quantum effects at a macro level as well. So there are observable macro effects. So you could technically, say, hey, BMW, Porsche. But then to say that BMW and Porsche are exactly the same because we're measuring different property, I think that is slightly not correct. Would you say that? That's okay? Because an electron has its own mass and a proton has its own mass. They both are quantum particles, right? But they have, if we measure the same property mass, right? Or if we measure the mass of a neutrino or a neutron, we're measuring the same particle, right? Or we measure their same angular momentum. Even though we're measuring the same property, even if we're measuring the same context, it is still a different particle. Would you agree on that?
Oh, I'd have to research that a bit. I mean, from listening to other professors speaking, they're basically saying if you measure the spin with two different observables, you will get a different spin you could spin up for one and spin down for the other.
Aha, so they're using the word observables. They're not talking about the particle. Because a spin of an electron is quantized, is differently to that of another particle, say, let's say a quark or a lepton or a boson, whatever, right?
Yeah.
So I think this notion is a bit confusing because the quantum contextuality does not depend on, or the identity of a particle does not depend on the context. It has to be, how should I say? You've got this particle physics, particle accelerator in CERN, right? And we are measuring all these quantum particles all the time. What we are actually measuring is, different levels of energy, different levels of spin. Yeah, but doesn't mean that, hey, just because we measure spin, it changes the particle. No, it doesn't. Because, for example, Higgs boson has a particular signature. So does, a quark or a pentaquark or things like that, right? So if we move on from here, please. And also, I just wanted to also say here, I think somebody in the group, talked about, oh, we should use photon because they travel and faster and blah, 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 right? So I think the entanglement is one of the most misunderstood concepts. And let me try to explain it in a very simple way, right? One of the most simple way to understand it, let's say you go to a fast food shop. Let's say you go to McDonald's, right? And you order a burger and you order, let's say fries, right? And you drive past the McDonald's and the McDonald's guy gave you a box. And the box has no label whatsoever, right? And now you have two boxes which look identical, right? And what happens is my mate who comes from, NASA, he said, hey, can you pass me one box? I need to jump on the spaceship, right? And that my mate from NASA, he took that box and he took it in a spaceship and he goes over to the moon, right? And it's about 12 midnight. I say, hey, it's dinner time. It's too late. I was waiting for you. It's 12. So NASA guys just reached at 12 o'clock on that space station. Now I open my box and inside is a burger. What do you think is on the other box?
Yeah, you're talking about the hidden variable.
It's the fries, right? But it does not mean that the information has suddenly traveled faster than the speed of light. No, it hasn't. It's because the two are entangled.
I know, but aren't you now just arguing the hidden variable there?
No. I'm not arguing that. I'm not.
Discussing it.
Yeah. No. So hidden variables. I think what hidden variable really meant is that there are properties other than angular momentum, other than energy density. There are other variables we currently do not have the technology. We do not really know about them. Even when we're talking about superposition, we are still, so when we put something in a superposition, so for example, in particular IBM quantum computer, when we put it in a superposition, it is still at the energy level. We're not talking about, orbital momentum. We're not talking about anything else. We're talking about at certain energy, which is where IBM quantum computer works. I think it's certain, I don't know exactly, some gigahertz or whatever, when they put it in superconducting bit, right? It's a wave. So it's up and down at the same time. And you're saying that's a superposition, but it does not mean that it is a superposition of all the different properties, because no computer exists, or, we're struggling with getting a computer that can operate in one property, but to operate across multiple set of properties all at the same time to give an outcome is even more difficult. And when we're talking about qubit, we're not really talking about a particle. We're talking about a system which has very clear defined measurements, i.e. is going to be in terms of a bit, is going to be 0 or is going to be 1. There's going to be nothing else.
Some qubits are particles, like the trapped ion quantum computer uses ions for qubits. You can use photons for qubits too. The analogy or the correspondence between a qubit and a particle is very close. It's only with IBM's transmons where you can't manufacture them so that they're identical, where the analogy loosens up a little bit.
I think I would argue that I think it would not be a good idea to actually attribute or to compare a particle to a quantum a qubit. Reason for that is this: a particle can have multiple of those properties, including the hidden variables that Eamon was referring to. But a qubit can only have one property, which is going to be either 0 or 1. It can be in superposition of those two states, but it can either be 0 or 1. It can't have angular momentum or magnetism and all of those things being measured at the same time. It will only have one of those two. Whether you're measuring it in electrical basis, whether you're measuring it in magnetic basis, whether you're measuring it in angular momentum basis, you have to choose one of your bases. And those two bases, it will always resolve to 0 and 1. So that is a clear distinction between a particle and a qubit. And I think
I don't know. When I wrote the program, I treated the qubits as particles.
So I think
all the math treats qubits as just one attribute, one observable of a particle.
So I think when I look at your code, again, I don't quite. I think one of the thing, if you can show your code, when you're measuring your code, because when you're doing the for loop and you go into the measurement, the moment you measure it, you lose all the quantum effects. What that means is that
that's not true. A measurement doesn't necessarily destroy the quantum effect. Measurement modifies the quantum state, but it doesn't always destroy it.
I would say that the measurement will, if you were looking at the particle side of things, or
if the measurement destroyed the quantum state, then the Peres-Mermin circuit wouldn't work.
Exactly.
Bob wouldn't have any information once Alice has performed the measurement.
And this is where when I looked at the code, this is the problem I was having, and I lost it halfway, is that the moment you measure it and you then try to put it back onto the quantum state, I think the IBM way of, again, please forgive me here, I don't know enough on, because I've not done much on that. But from what I understand is the moment you measure it, you lose the quantum property of that qubit. That's number one. Number two.
That's not true. If you look in Quantum Computing and Quantum Information by Nielsen and Chang, they show you the projection operators that take the state before a measurement and give you the quantum state after the measurement. There is a quantum state even after measurement is performed.
So I'm coming to that next part. The next part is that if you want to then put that state back into the quantum state, I think
you can't go back to what you had before the measurement.
No, I'm not saying you can. I'm just saying putting in a quantum state. I'm not saying you can go back, because you clearly can't, because it's a quantum state, right? But it has been now flattened out to a 0 or 1, right? Because that's the only output you get out of it. And if you have multiple of those, you get a binary out of it, right?
Well, these are what I'm saying is qubit measurements, so they give you more than, there are 4 outcomes, not just 2.
Yes, so it will form a binary, right? It will form a binary digit, binary number, whatever that would be, but it would be a combination of 0 and 1s, right? And you can interpret it as a binary. So that's part one. But what I'm saying is, if you want to,
it's a superposition of 0s and 1s. It's not just a
yes, that's the measurement part, right? Because when you do measurement on a superposition, it's a median over number of states. So again, I'm not disputing that part. What I'm saying is that once you have taken out, once you've taken the measurement, what I am saying, again, I could be wrong from what you're saying, is not only that measurement, that state is lost, but then to put that thing back into, now I'm not saying back into the same state, I'm saying back into quantum state. You have to first reinitialize the same variable, number one.
No, you don't.
And then
you have a quantum state even right after the measurement is performed. that's what these projection operators do. They tell you the quantum state that you get. It depends on what the measurement outcome is, but you still have a quantum state even after the measurement is performed. That's like really fundamental.
Okay. Well, I don't know. I mean, I think from what I understand that once you measure, you cannot have the quantum state is lost.
No, it's just modified. It's projected is the verb that is used. There are these projection operators. There's one projection operator for each measurement outcome. And depending on what the measurement outcome is probabilistic, but given a particular measurement outcome, the resulting quantum state is determined by that measurement outcome. That's the reason why this circuit works. And this is the reason why they win the game, is because
but the circuit doesn't
destroy the quantum state.
No, but the circuit doesn't work. When you use it on a real quantum computer, it doesn't work.
Well, that's just a matter of noise and engineering. It's not a fundamental quantum mechanical limitation. It's just an.
But I think from a
problem.
quantum mechanical fundamentals, I mean, it is a given that once you make a measurement, the quantum state is lost.
No.
But I know what you're saying.
Not.
You're
if
saying
you
that
look
it's a
in the book
projection.
and read about it, you'll see.
Yeah, I mean, aren't you just it's like measurement-based quantum computing, right? Whenever you measure 1 qubit, you just trace that 1 qubit out of the state, but you still have a state left.
No, that's correct. That's correct. Yes.
Well, we're going to have to continue this offline, I think.
So I think that what I was trying to say earlier was I think there are, and the reason why I wanted to open for discussion is, to learn from it and understand the viewpoint. And I think one of the things that is very fundamental to this is that no, the particle does not change based on context, because no matter what you the mass of an electron is different to a mass of proton. Similarly, magnetic property of an electron is different to a magnetic property of a quark. So even though you're using the same context, you do not, the particle does not change just because I'm measuring a different context. And I think really very important to understand superposition when we are doing in terms of quantum. In actual physics, you can have superposition of, across multiple properties, no problem whatsoever. But in a quantum computer, and the quantum computers will have in 10 years' time, I don't think we'll have the technology to measure superpositions of multiple states over many different variables, hidden properties. But forget about hidden, I mean, even the known properties. We're already struggling with the properties we know. And the third part is, no, there is no faster than light travel. There is no travel whatsoever. In fact, travel does not involve at all. It's a matter of when you entangle two systems, you're essentially, presetting it in the sense of like the example I gave of burger and the fries, right? And no matter how far you take them, if you open one box, i.e. they were both in superposition state, the moment you measure one, the entanglement is lost and the superposition is lost because now you know what's in the box. It's a burger, yeah? And if it's a burger in this box, that means there's fries in the other box. And therefore entanglement is lost, superposition is lost. There is no, we know the cat is dead or alive. So superposition is lost, entanglement is lost. Superposition and entanglement are very connected to each other. And no matter how far you take it, there is no traveling involved here.
I think we're going to have to agree to disagree.
Okay. Yeah, that is all. That is all. I mean, I just wanted to, understand what. So yeah, that is all from me. I wanted to say thank you for that.
Yeah, thank you for the question. Helen, are you still there?
Yes.
Right. It's just I don't know whether you wanted to wrap up or you want further questions.
I have a question.
Oh yeah, go on.
Is the previous discussion and the presentations relate to once I measure the wave function collapse?
That's correct.
If yes, how can I understand the previous exchange or discussion, because it looks like Sam and Anna have different view, which could be the difference between theory and practice, because Anna demonstrated that in practical programming, you can deal with these concepts, whereas Sam is sticking to the principle of measurement destroying the wave function.
The
So maybe
measurement
Anna
doesn't
tells
destroy
me,
the waves. The
maybe Anna
measurement
tells
doesn't
me,
destroy the
just a
wave
minute.
function. Measurement modifies the wave function.
Yeah, that's what I was about to say, that your interpretation of wave function collapse is it's collapsing, not disappearing, but being modified. And I tend to buy that. However, it seems to me like a new perspective, which I can admire or not.
I think that's a very good analogy. I like that. However, I will only say one thing is that, and I hope this, I have to go and read on it because I would be surprised. But then, Anna's program hasn't worked. That's the whole thing. It hasn't worked. Now call it whether it's noise or whatever in the system. The program hasn't worked. But then, it's always, as a scientist, we should not be, like stuck in what we know. We're always learning. And I think I like that maybe it just gets modified, right? So I think I quite like that. However, Anna's program hasn't worked, and it does work, I hope. But, just wanted to say that. So thank you for that.
So where are we?
Well, she, as Anna mentioned, she's going to write, program and check it if it can be worked, or wait for, she thinks it's a problem with the quantum computer because of noise or other means, and she'll keep experimenting it, perhaps present some other time.
I'm going to show you something. This is from Quantum Computing and Quantum Information. Right here. The state of the system after the measurement is, and then they give this. This M is the projection operator, which I coded. It's derived, it's the unitary, it's 2 rows in the unitary matrix. This is a normalization factor. This is the wave, this quantum state before the measurement, and this is the quantum state after the measurement. This is the theory of quantum mechanics. And quantum mechanics is on a sound basis. It's not, there's no doubt about the truth of these formulas.
Can we get that reference?
If you give me your email address, I'll email you the whole book.
Or maybe linking it in the chat?
No, I can't give you a link to the book because I don't have the link, but I have the book and I can send it to individuals. If I publish a link to it, I think I might get in trouble with the author.
Yes, Anna's correct on that. She might get in trouble. That's right. Yes.
Okay, sorry, I wasn't aware of that copyright stories.
What is the title of the book, though?
Quantum Computing and Quantum Information.
Okay, so we can find
Is that
it
Nelson and Chan?
Yeah, Nielsen and Chang, Quantum Computation and Quantum Information.
Is that from by Cambridge University? Is that right? I think I have this book.
Yeah. It's highly referenced across.
Yes, it is.
Very highly referenced. Yeah.
Agreed.
I think I've read it, but I mean, again, with regards to that particular page, I need to go back onto it. But as far as I know, that when you do normalization essentially means, normalization is a mathematical term. In physical terms, it means nothing, right? But if you want to visualize normalization, normalization is you are evening out the states. So if something is in superposition, you are taking it as a median of all the crests and troughs, and that's your measurement. So you're flattening out the wave. That's what normalization really means.
No, normalization
However,
is not an averaging process. The state vector points in the same direction before normalization as it does after. It's just a scale factor.
I need to look at it.
Yes.
I think that there is a interpretation that depending on your background, right? So if you get from statistical background, you have a particular view of it, and physics-wise, you have a particular view of it. I think unless you read that, go back and read that text and maybe actually understand the nuance, it may not be very apparent, like what exactly it is. I think that will set the context for you, at least. That book will give you, probably you'll recollect, what is the right way.
There's a question from Bennery. Is there any limits on the numbers of measurements of a qubit?
The number of measurements. Good question. You lose information every time you perform a measurement. So it seems like, well, no, I mean, you could have like a Stern-Gerlach apparatus where you have a particle with its spin pointing up in the z-axis, and then you measure it horizontally, and then you measure it vertically, and then you measure it horizontally. Or you could do it with photons, measuring the polarization, and just keep on adding more and more layers, more and more steps, indefinitely. So the answer is there's no limit on the number of measurements, except in practical engineering terms, as we discussed, these quantum states, they interact with the environment, and the stray vibrations and magnetic fields eventually just interact with the particle and modify its state. That's an engineering issue.
It sounds like it would be an interesting experiment to like run on IBM, where you just like when you do a measurement on a qubit, it resolves it to whatever basis you're measuring. But if you measure it again, it should be the same basis state, right?
If you measure it in
and
the same basis, but if you measure it in a different basis, you'll get a superposition.
Sure, but if you measure it in a basis, you'll get a 1 or a 0, or you'll get a plus or minus, or you'll get an angle. But if you measure it again, you get the same answer. It's been resolved.
Only if you measure it in the same basis. If you measure it in a different basis, you'll get a superposition.
Right, but if you measure it again in the same basis, you should get the same answer. So
you will get yes, you do get the same answer. That's correct.
Okay. So the experiment would be to see how many times can you measure it on an IBM, running it on a real IBM hardware before the noise kicks in and changes it, and then try to measure how many iterations you can go.
Well, in the Peres-Mermin, we performed 6 measurements, and it completely randomizes everything. Not completely, but you lose 80% of the accuracy.
Right, but if we just simplify it to a simple program that's all it does is it initializes a qubit. Maybe you put it into superposition, maybe you don't, and you just continue to measure it to see how many measurements you can get before it changes.
That would be a very interesting experiment.
Yeah,
very easy to do. We'll do it.
Let's do it.
Yeah, I think IBM would have already done that, surely.
Oh,
they have, and they publish it as a measure of their fidelity. So, I mean, that's a given. But I think it's in if you measure the same basis again, as we already know because it's proven, is that you always have the same outcome every single time. Of course, the noise then had some, but then I think they have got some error correcting bits that also make sure that you get the same reliability.
They're still working on that error correction. They've got a long ways to go.
Wow, great questions, everyone.
And there's another question from Rob. Can you include crops operators in your simulation to test the fidelity to see if it agrees with the experiment?
Unfortunately, I don't yet understand cross operators.
Yeah, I haven't worked with them too much. I know that if you use Circ, Google's Circ, that they have cross operators that you can use. And so all those do is they're just an operator that adds they're not not a pure operator. So it just adds noise onto your qubits so that you actually lose information just through noise. So anyway, it just gives you a way to sort of test the limits, like how much noise can you add before the algorithm doesn't work anymore.
And also, I think as a matter of making your program more robust, you can actually add your own error correcting code in your own algorithm. So you could have a subroutine that every time you perform a measurement, you could have your own error correcting mode. By the way, somebody asked a question just now on the error correcting, Santanu, about blind error correction. Now that would be an interesting one. What we do know is that currently the way error correction code works is pretty similar to the way that it does in classical computing, or those what do you call it, Hammond's code, or I can't remember. Basically, when you take, so if you've got a 7 bits, you then measure all of them and make sure that you have a 4 out of 7, for example, are pointing to the same thing, which means you have win by consensus, that kind of thing.
But you need, they're talking about like 100 or 1,000 qubits to protect 1 qubit from error.
That's right, the physical bits and the logical bits, right?
Although there was a recent presentation on the Qiskit seminar series where they talked about error correction on a Falcon machine, which has, I think, 27 qubits. So not everybody agrees that you need 100 or 1,000. This particular presenter seemed to feel that he had significant results with a couple of dozen. I don't know how he did it. I'd like to do it. I'd like to, like I only use 4 qubits for this program, and public access will give you 7, and probably without paying much, you can get a couple of dozen. So if there's a way to use ancilla qubits to protect the state, I would be very interested. I'd like to try it.
I think one of the fundamental that I'm observing is there is a disconnect between physicists, quantum physicists in particular, who understand this from a quantum world, and then the quantum computing and the computing people. So computing people have a certain understanding of, because when we form an intuition of the subject. We are always forming an idea as how things work and all that. So I think, and when you apply this on the quantum where you're only operating in one set of base is not the correct word, but let's call it a property, then I think it's the translation from the quantum to the quantum computing, which has a very limited set of property, because quantum physics is a far broader subject, whereas quantum computing is a really small subset of it, which applies to 0 and 1 and a particular set of property. And that's where the disconnect is. And to me, I'm also learning. And I think if there was something good out there which connects the two dots, that would be great to know.
Well, quantum computing is about quantum information, and nuclear physics, solid state physics, condensed matter physics is an application of quantum theory, as is quantum computing an application of quantum theory. So that, like, if you look at what Scott Aronson says in his best-selling book, that quantum mechanics is really just a framework for understanding probability, and that nuclear physics is an application of it, and so is quantum computing.
By the way, Anna, I will try to reach out to you regarding your compilation thing, because in the past I have written compilers, so I might be able to help out. But then again, I don't know what sort of background is required, but it'd be fun.
Well, if you have experience, if you can parse, if you can use a parser, I think you would be qualified. I'd love to have your contact information.
Sure, I will email you. I will email you.
Okay, it's Anna@quantumwithanna.com. Who is speaking, by the way? Who was that? You're muted, Eamon.
Yeah, his name is Zoom Caller. He's a regular. I don't think you've ever given your name, have you, Zoom Caller?
I just did. I did say Sam, didn't I?
Oh, someone else did say Sam, actually. Yeah. In fact,
That was
I
me.
remember that.
That was me earlier. That was me at the start of the conversation.
Right? Oh, right. Oh, you mean, I didn't realize that was you.
Yeah.
Oh,
and,
sorry.
Oxford University, if you remember from our last conversation.
I do remember. Look, thank you, Sam. And do get in contact with Anna, because I think you would be very helpful. Sorry, Sam, I didn't realize it was you.
No, it's no problem. I think I might be doing a presentation at some point in time, because I just finished writing a paper, and what I've written right now is it kind of build on the intuition of quantum and the quantum computing, and it goes through the whole Shor's algorithm, and and answers a lot of questions that I realized while coming to these seminars, as well as the disconnect between the two. I'm just trying to work out the logistics, and today is a really friendly crowd to I asked some very difficult questions, probably controversial. Apologize for that, but then
that's what we need. That's what we need.
I mean, as a scientist, I mean, I'm not trying to kind of challenge anybody. We're trying to learn, but only by asking questions can we learn. And sometimes we are not I found geeks are, well, I will not call myself geek, but people who are in this realm, they're not the most politest of speakers, and I apologize for that. I don't know how else I could put it.
No, fair enough. Well, you'll find us very accommodating to your points of view, as I think you have this evening. So That's wonderful.
Thank you.
So when Sam will be presenting in our forum?
Yes, Dev, I will be, I think I'm going to put together, I'm just trying to put together something and then I'll reach out to Helen. I communicate with Helen often, so I will reach out and probably put something together.
Oh, good.
Looking
forward to it.
Yeah, may I ask a question? My name is Seshu, by the way. I'm joining for the first time. My question, I'm a computer guy, so it's one of those geeks that you're talking about, right? So, so from a computation angle, one of the things that I find very interesting is when you're given a true application, when you want to do a real world use case that is impacting a particular company, let's say finances or some other area, there's a lot of literature that has been written around and a lot of algorithms have been defined. But what I find it difficult is to estimate, to have a resource budget, right? So upfront, like how many qubits would it take? How would be the depth of the circuit or the parameters of the program that you require to solve the problem? And those estimates are not clear or the methods are not clear. Do you know of any reference, a good reference for me to explore any pointers in that direction?
I don't.
So, Sash, was that Sash?
Seshu, yeah.
Seshu, hi, Seshu.
Yeah, hi.
I think from my perspective, the way I see it is, right?
Yeah.
When you have a classical program, then you use certain number of computer memory, you use certain number of bits, right?
Yeah.
When you're writing in a high level language, let's say a finance program is generally written in Java or C# these days, a bit of Python as well. You're not really thinking on those terms. You never think of how many bits does it require, how much memory does it require. Although memory, yes, but you often do think of precision. So for what I mean by precision is when you're representing a billion, right? A billion can only fit in a certain register, correct?
Yeah.
So similarly, when it goes over that, you actually truncate it and you handle two different registers, correct? Yes. So with quantum, you have to understand that in quantum, whatever is happening, so if I look at 2 raised to power 2, which is 2 times 2, right? That's 4. And you will need how many bits for that?
Yeah, it's an exponent, right? So I get that.
Yeah. But the thing with quantum is that you can have, so
please, I get that.
Yeah.
The constraint that you have in real world is that you are looking for some advantage. Let's say I use quantum for trading, right? So what's the advantage? You've got to have a business case to justify that, right? What does it provide as a relevance? Because there are a number of applications we can talk about. To understand the relevance for a particular area, you need to see where is the advantage. Is it in terms of resource? Is it in terms of speed up? Is it in terms of a different pattern that you get from quantum? And when we look at that, the initial things that we do generally tend to test is how many would we require. So for example, if you take Shor's algorithm, and you want to estimate, people will say, you require a large number of qubits, right? So there is some kind of an estimate that people have, and I just wanted to know, is there some guidance around that, or is it in the, you require too much specialized people to look at that? Is it simple enough that I can understand, or something that is very complicated?
If you understand Shor's algorithm, which is my presentation that I hopefully will be doing, it actually covers some of this stuff, right? Because
okay.
Because
I'll then attend your presentation.
I haven't done it yet. And hopefully when I do present it, I cover some of this stuff, right? And one of the things that you have to understand in Shor's algorithm, if you've read it, it's about period finding, correct? And the period finding from a point of interference. If you try to run it on a classical computer, you have to do one step. So you do first spirit finding, the second, the third, the fourth, the fifth, right? But in a quantum computer, because of the amplitudes, you can have all of that in one go. And this is the advantage that it offers, because you can have all of those periods submitted in one single step.
Right, but today you can't implement that, right? There is no implementation.
You can do it on small number of prime factors. You can't use it on 128 bit, or 256 or something like that, right? But when the quantum computers reach, for example, 1,000 qubit, proper 1,000 qubit, then it will break every single algorithm, both symmetric and asymmetric. And this is where the greatest worry is.
Yeah, I get
right?
that. I understand that. Yeah.
And
yeah.
what can you achieve? What kind of programs can you achieve while you're doing that? And this is where my question earlier with Anna was about measurement destroying the effect, because the point is that measurement in a quantum computing is a very expensive
phenomenon. Yeah.
Because when you measure something, you're literally, you are destroying all those amplitudes, and you are flattening out your output, right? And this is an important. This is why a measurement should be used as a last resort. Because if you're going to use measurement, why not use a classical computer instead, right? And this is where the whole advantage of quantum computing lies. And hopefully, if I can do my presentation, but then
I'll wait forward for that. I'll look forward to it. Yeah, for sure.
Yeah, me too.
Yeah, yeah.
I know you guys are going to make it very difficult for me, right?
No. We're all in the same boat.
Yeah, not at all. We're all learning.
We're all learning.
If I could get back to quantum compilers, since I think we're kind of running long. If for those of you that are interested in quantum computing tool chains, compiler technology, I gave a talk. I put the link in the chat. It's probably way up there by now. To a recording which is on YouTube. So please check it out if you're interested in compilers. I also have lots of experience with compilers, and hopefully we'll be able to add to the technology soon.
Sure.
So
excellent. Good on you, Ron.
One question that I've been asking myself lately is, how does one go about comparing the performance of a quantum computer to a classical computer? Is it even doable with the amount of preparation work that has to be done on the data, converting from a classical set of data that you've collected to a quantum representation, then running the quantum algorithm, and then bringing it back into the classical space to try to interpret what the results are? How does that, and then the wait time on a quantum coprocessor, basically, how do you compare that to a classical algorithm where they're very highly optimized, the algorithms have been thought about for a long time? So we have two completely different worlds, and we're trying to compare them to say, oh, well, obviously quantum has this advantage. There is an advantage to quantum computing. It's just not clear what that is at the moment, other than, well, now we have a place where we can get a lot of randomness, a lot of entropy right there, and use that to make maybe better guesses. But that's not something you can measure. It's not something you can put a number on, right?
Well, it's really hard to compare a quantum computation with a classical one, because the problems they address are so far different. There's only a handful of quantum algorithms that are really established, whereas there are, a gazillion classical algorithms.
Right, that's the question. Can you even compare those two worlds? Does it even make sense to ask that question, right?
I think it might make
Can I
sense
try to
ask the
answer that with
question,
an example? I'm sorry, go ahead, Anna.
I think the question makes sense, but I don't think the state of the art in quantum, we don't know what quantum computers are good for. We don't know what problems they solve more effectively. designing a quantum algorithm, as I discovered with Peres-Mermin, is very challenging, and it hasn't been done for very many applications.
If I could offer an example, a number of people are using quantum computers to solve real world problems. One of them had to do, and a lot of these real world problems seem to be using the D wave annealer, because the main algorithm that is being exploited is optimization for various algorithms, and also in quantum machine learning, optimization is what's being exploited. But to give you an idea of what's happening there, there's a company who uses the D-Wave machine to come up with better routing schedules for a trucking company. It's kind of the traveling salesman problem, which everybody knows how difficult that is. Well, they are happy if they get a 6% improvement, but they still haven't solved the problem. They're using quantum to do 6% better. Now, if you're doing this for a trucking company that burns $1 million of gasoline a day, 6% is worth the effort. So, and that's where the state is right now.
And Ron, I take it that's not commercially available yet.
No, there are people who are using the D-Wave services. It's not cheap, but they're justifying that by improving a particular customer's routing by 6% and saving them 6% in fuel and time. That's using
exactly programmable, right, Ron?
Yeah, but it's trial and error. They're not done. You're never done with an optimization problem. You keep trying to make it better, right? Yeah. So that's where we're at right now. So the original question is, how do you measure it? You have to just try it. You have to have the budget to try it, I guess, in these days. So,
if I may chime in on that. Yeah, so I think spot on that, Ron. I mean, the D-Wave computing is different to it is a type of quantum computer, but it's a thermodynamic quantum computer rather than a gate-based quantum computer that Microsoft or IBM or even Google are developing. And some people argue that the adiabatic quantum computer, as it's called, or the thermodynamic quantum computer, it's called, is not a true quantum computer, but it has been in existence long before IBM's quantum computer came, or even the CERC came and all that. And then with regards to that particular scenario, they are using it in Beijing transportation system. And also there's a guy from a group of doctors from India that developed an algorithm to schedule hospital appointments and nursing system, nurse appointments, and how the staff will work over their COVID period and all that. So that also offered an improvement. The Beijing system apparently offers some improvement. And you have this trucking example. So this traveling salesman problem being optimized, or some countries, I won't name who, are using it to deploy military, for example. So how can you use a military to be at X number of places and to cover distance when an eventuality arrives, for example, or things like that. So that is, obviously military. But I think in general, if I may take it slightly one step further, there are limitations with classical computers, we know, because of memory or the state space that it can represent. Which is why Feynman said that if you want to mimic nature itself, you will have to use a quantum computer, because nature itself works as a quantum computer. So if right now we don't have quantum computers, gate-based quantum computers, not capable enough, i.e. they don't have enough number of qubits or the error correction or whatever, that we can do something practical that offers real value in the gate-based system. Although there are some, I remember 3-4 months ago, there was a protein that was found using IBM-based quantum computer. I don't have the reference for it right now, but I believe that is correct. So in chemistry, it is being used quite a lot, even what we have currently. But I think the greatest advantage that will come is in the field of, which is yet to be realized, is going to be in the field of cryptography. Number one, we are already seeing that. Quantum random number generations are, it's like the base of almost every algorithm. So for example, if you look at your AES, which is advanced encryption scheme system, or if you look at, almost every TLS to even your PKI, all of them require a random number. And these random numbers are generated in very, in a cycle called the CBC cycle, which have their own attacks. But if you can have a true random number, then obviously it becomes very difficult to guess. And one way to understand this is, imagine there's a maze which has one entry point and one exit point. And if a classical computer was to run this, if you were to write an algorithm, the classical computer will go each of these mazes step by step, each of these paths, and calculate and come out on the other side. Whereas if you look at the quantum computer, imagine dropping a bucket of water on the top of that maze, so the water exists in all the places at the same time, and therefore it knows the path immediately. Now that is the crux advantage of quantum computer, which classical computer doesn't have, because classical computer need to evaluate every single path, whereas quantum computer can evaluate all the paths in one single step. It's only when you measure, what that is, what the output is, right? So that is the major advantage that your quantum computer offers. We don't have, that water, as I call it, the reason I gave the water example, we don't have that many number of qubits to actually really kind of demonstrate something. However, there are small things, we can, for example, factorize number 15 using quantum computer. It might seem like very childish, but this is the same thing happened for our classical computers too. I mean, we've gone through that long journey when computers used to be housed in a very large building, and what they used to get very tiny 1 or 2s, and then you have Enigma machine. So this is what the quantum computing is going through the same phase. And once there are enough traction on the subject, enough investment is going into this, and people who are putting investment, they clearly realize, that this is a great advantage to have. And this is why it has to go through this same cycle. Once it has gone through the same cycle, we will find as more and more people get interested into it, more investment, and suddenly we will have a eureka moment when, you see quantum computers everywhere, and we'll use it without even thinking about it. And in the same way, we will kind of change all our way of thinking. We'll change our encryption standards. We will change a lot of things. But for that to happen, it has to go through that. And one of the biggest beneficiaries of this will be in the space of medicine, chemistry, and cryptography.
I agree there. It certainly feels that quantum computing has a definite advantage. However, the engineer in me wants to be able to write down a number. And right now, it's very difficult to do that. You can't sit and say, yes, a quantum computer will give me a 15% advantage on this. It's a guess that it will. And I've heard about the optimization problems and the fact that running a large linear programming system on a classical computer and then running a similar type of where you get essentially the same representation, and eventually you'll get the same the results out, takes less time on the quantum computer. The quantum computers appear to use less energy, even though you have these dilution refrigerators that have to keep them cold. But it takes a supercomputer to go through and do a similar type of process. So you're expending a huge amount of energy, lots of resources involved. But how do you write down, I'll get a speed improvement, I'll get energy efficient improvement. We're not there yet. We can't. It's difficult to make that comparison. I've not yet found one algorithm where I can say, okay, I'll run it on a classical computer, I'll run it on a quantum computer, and that'll let me measure how long it took, time savings, step savings, memory savings. I can't write down the numbers. But I know the quantum computer looks like it's a lot more efficient. I'm just not sure how it's efficient yet. Right?
So I think if you look at addition of two numbers, right? You can do the addition. So you can do all the classical operation that you do in a classical computer. You can also do it in a quantum computer. So if you want to add two numbers, you will find that it actually takes less energy, removing that part of what's called your freezing bit. Because technically, quantum computers are sort of reversible computing. One of the problems we're having with our data centers and all those things is they generate massive heats. But one of the biggest advantages of quantum computing is that it's a reversible computing. Right? So it's eventually going to save you.
Hold on a second. I would argue that the CPU in my laptop is faster at adding two numbers than the quantum computer is right now. Especially because you're only running the quantum computer at 100 cycles a second. Or I'm sorry, 100,000 cycles a second. You can only shoot that many circuits, whereas I'm doing billions of additions a second. So that's not a really good benchmark.
But it's not a like-for-like comparison either.
No. The issue is in real problems that we see, right? Like if you go to, let us say you want to do derivatives pricing. I'm just taking finances as an example, right? Or you're doing molecular chemistry, whatever, right? In real world, when you go to industry, most business people would ask for quantification or benchmarking an advantage. If you take portfolio optimization, I know D-Wave has done some implementations of that, whether it is traveling salesmen or unconstrained optimizations that they have done, some linear integer programming, those kinds of examples, right? They're mostly toy examples.
I'm going to have to drop off. I have to prepare for tonight's event.
Yep. Thank you.
Thank you,
Thank
Anna.
you very much, Emma.
Thank you so much.
Okay.
See you tonight, Anna.
Yeah. So the issue that we have is there is no clear benchmark or there is no clear way to estimate the advantage. What kind of advantage are we talking about? How do we quantify it in business terms?
I think in the literature, there's a number of references to the quantum advantage having the ability to attack an exponential problem in polynomial time. And that's a very simple thing. And that's probably the place you need to start.
But there's no benchmark. What I'm saying is that there's no place.
For Ken, you're absolutely right. You have to look at real world, people that have been out there in the real world and just look at what the results are. And it's suboptimal. It's not, if we had perfect quantum computers, might be a lot better. But in the example I gave where 6% was justified because of the budget somebody was improving.
Oh, that would be great. That would be an acceptable advantage. I get that. But you can't sit down and say, yep, we're going to get that ahead of time. You got to go through, try it and see whether you get it or not. And even then,
I agree with you.
It's really hard to construct. Like I said, you can't write two programs, or you have one problem. You implement it both in the quantum sense and a quantum circuit and in a classical program and run the two against each other and see, okay, it's a horse race. Who won? And that's the question. Who came out of
all I can say is you study the quantum algorithms that for optimization, for estimations, for like the quantum Fourier transform, and you get some sort of idea of what the speed up might be in a perfect world, but you won't have any way of knowing what you'll actually yield based on current hardware technology.
Yeah. So here's the thing, though, right? So first of all, we're expecting something from an immature technology. So one is the theoretical part of it, and one is the technological part of it. This technology is still developing. But you might say, but that's no excuse, right? But here is another way to look at it. if you look at, some program that you have written or the trading algorithm program that we're talking about, have you actually, if you were to really want to do that, you have to analyze what is the current state of play in your own application. Because if you have written a program in Java,
I'm trying to do that right now, actually.
Yeah.
So yes,
exactly.
I understand the
That's
problem
part
that you're talking
about. So hear me out for a minute. Yeah, please. So first you have to break it down, what sort of computational resources in terms of bits, in terms of memory, in terms of step, you have to quantify all of them. Once you have done that, you have to do the same exercise with a quantum computer, theoretical basis, right? So for example, if I'm running this program, how many qubits would I need instead of bits? You will clearly see an advantage that you'll need less number of qubits as opposed to bits you're using, number one. Number two, how many steps would I be taking in the program that I've gone in my classical world? Hey, I'm taking 20,000 steps, but hey, in this quantum computer, it only takes 20 steps. There's your given advantage. So I think people can actually go about writing a research paper where they can analyze one particular program, but to analyze individual program, one has to look at their own set of problem and break it down and perhaps do a presentation, right? And that way somebody can benchmark this, then a lot of other people will start to do that. But then again, to do such an exercise itself is not an easy task. It's very time consuming. How do you justify that to a business? I need to do this in order to prove that the quantum advantage. And this is a chicken egg solution, right? But then from a research point of view, it's an exercise worth taking. And every program is different. And one has to go through, their individual program. There might be instances where, a quantum computer is no advantages than a classical computer. They both perform at the same level, right? And that's a difficult one.
Have there been any papers? I've seen the marketing literature on how wonderful the quantum things solve these things, but have there been any actual papers explaining the advantage for the linear programming and the speed up on optimization?
I have no idea, but I know Shor's algorithm, which is the most studied one of them, it does have some of these examples.
Agreed. I know it's there. And like I said, it feels like quantum computing has a definite advantage. It's just, I can't explain it to somebody who's going to write a check for a quantum computer yet.
JP Morgan
that's absolutely a problem. And again, you have to describe it in terms of complexity. Quantum has the promise of being able to solve problems that are intractable in classic computers. Again, by converting something that runs in exponential time to polynomial time, but there are other algorithms. I wish there was a resource what you're looking for, but again, all you can do is learn as many of the algorithms that are out there, find out what they're good for, and just be on guard that you're not going to get the optimal performance today. Maybe when the quantum hardware gets better and less noisy, it should get better. But
well, there's probably an advantage today too. It's hard to say. Like you said, the 6% improvement on a large scale problem is wonderful. That'd be fantastic.
Yeah, but it's only going to appeal to a certain class of clients, right?
Right, but it's also, how do you find a test case where you could get that type of a comparison, right? The people who are doing those don't want to share their information, but it would be really nice to come up with a network or something like that where you can do an analysis on it. I don't know if there's a data set out there where we would be able to run something like that as a comparison. I think it would be very interesting to do so.
Yeah, there may not be a data set, but I've sat in on a number of presentations where people explain what they're doing, and again, they're coming up with around the 6% improvement, not just in transportation, but in, people have mentioned quantum chemistry. There's a company that is doing drug search by using quantum on the front end to make better guesses at which molecules will do better in a certain experiment, and then the quantum picks molecules with a better estimation, and then they hand it off to a machine learning stack to process it. What is the advantage they're getting? Well, it might only be that instead of looking at every molecule they have in their database, they're only handing maybe 10% of it to the machine learning stack, and they're getting good results there. But what is that exact speed up there? They don't even care.
A better
They just
guess
know-
earlier. A better
Yeah.
guess earlier seems to be
Yeah.
the main thing. I mean, we've been doing Monte Carlo stochastic processes, non-deterministic things for a long time, and it does give us an advantage. It's really hard to, and like the traveling salesman problem.
Here's another example. You mentioned Monte Carlo. In quantum image processing, there is a quantum supersampling algorithm that replaces Monte Carlo for like scale reduction of an image. And it's not faster. It's not at all faster, but it gives you better results. Okay.
Interesting. Right. So that's another way that you could measure the improvement. And that's
Yeah.
fine too. It's just, I'm wondering if anyone has seen any papers on this. I mean, I see the marketing stuff and the slides and presentations saying, yeah, it's much better. We do all this great stuff. And it's like, okay, so how about some data? Like what's that actually mean? And I haven't seen anything. I've been looking. I've been trying to come up with a problem where I could do that benchmark. But the quantum computers available publicly, for free, are too small to run some of the serious problems. So you're not going to get a serious improvement, perhaps.
Yeah, I wish you good luck in your search for that information. And again, there are a number of groups like this where people come and talk about what they're doing.
I know. I've been listening to some.
Try to find those, and a good one was Southern California Quantum Discussion. He has transitioned more to the medical side, but if you go back and look at his stuff, he's got all, and he records everything. He had a lot of people come on and talk about what they're doing with quantum chemistry, molecule finding, the traffic routing. There's a number of things there you can go look at. You're just going to get a feel. But in any case,
did you say it was Southern Cal or South California, or what is the
Southern California Quantum Discussion by Kevin? I can't think of his last name. But you can find him on Meetup, Southern California Quantum. So it's been a great discussion. I also have to bail. Hopefully you guys will pick up some of these topics in future sessions. Everybody have a great day.
Thank you. Thank you very much.
I noticed George Zipperlin has a question. He raised his hand earlier. George, do you have any question?
No, I just had a comment that on the theoretical side, there is a lot of literature about both classical computational complexity and quantum complexity. So there's a lot of papers by Scott Aronson and others in this area. But I do understand that the question was more about in the real world. But for instance, there's the quantum complexity zoo that has a vast number of these problems in their time and space complexity, both quantum and classical. I could put that link up there.
I've looked at that. The problem is some of the coefficients that are left out of the big O notation are enormous. So it's like, well, yes, the algorithm has a growth rate that's much lower. However, the overhead of doing that is huge. So it's not a practical, I mean, it's useful, it's instructive, it's helpful, but it's not a practical thing yet. It's not something I can, right?
Yeah, I'm sorry if you're already aware of that.
No, that's all right. I understand. I've been trying to do a lot of research on this, but I was very curious at the Peres-Mermin that this is something that could show, it's a simple test, but when you go to actually run it on the quantum computers, it doesn't work right. I mean, the simulator is one thing, but actually run it on hardware, It was very fascinating. We could reduce it down to 9 variables and explain that there's a significant improvement. There's a serious advantage right there. You can win the game every time, right? So it's like, unfortunately, it doesn't work in practical terms. I have to use a simulator, and it's like, well, yeah, that's okay. But it's still not that advantage. I thought quantum computing would be, you know, this wonderful. And it's as I said, it's still new technology, even though we've been working on it for 50 years. Seriously.
No, I think we haven't had quantum computing. We had the quantum theory for over 50 years, but we haven't really. Nobody has actually really technically worked. I mean, yeah, I mean there were these
since the 80s,
wire, you know, but then
since the 80s, they've been trying to build things. So
yeah, we haven't really had something like CERC or IBM, and real development on these when these big companies really took interest is only last 10-15 years, no more than that. So it's pretty early, I would say. And I mean, I'm quite passionate, enthusiastic about it, even if this to me is like, it's just so much full of hope and so many things. But you're right that the stage we are at right now is pretty basic, but have some faith, we'll get there. But then quantum phenomena itself, which is pretty old, there are a lot of working things coming out of that, and already quantum radar, okay, but quantum sensor, which came out of the Birmingham University 2 years ago, is a real thing. It's not quantum computing, but what is a computer? I mean, computer is something that measures something. If you think of it as a quantum computer, then it is a quantum sensor is a quantum computer, the one that's from Birmingham University I'm talking about. And similarly, there are a lot of things going to come out. Science is progressing at a rapid pace at the moment. But some of these problems that we are talking about, which are, one of the things you mentioned, are people really going to share the advantage they have immediately with others, something that are at a commercial scale? And that's another challenge. Maybe people do have those. People are not talking about it because not everybody is into that research set of mind or sharing kind of thing. We don't know that. But I think the maths behind it is solid. The theory is solid. And we've got something that is out there. It's just a matter of time. And I think 5 years passed like that, because I know how quickly my undergraduate went or my master's went and all that, so we will see something for sure.
I think so too. It is a very exciting thing. Otherwise, I wouldn't have gotten up early to listen to this talk. And there's so much promise there. It's a question of whether we can, the noise floor is low enough to actually get useful results out. And it keeps improving, and the number of qubits keeps going up. So there's hope. It's like, okay, when can I actually show that there really is an advantage, right?
And there's one thing I like to, and I put this in my paper as well, which is a slightly humorous take on this, right? And one is this, that let's say all of this is fake, right? We never get to see a quantum advantage, but there is a flip side of people who are entrepreneurial, business side of things, right? And that is this: if trillions of dollars get invested into quantum computer, which it is getting through, if the money goes from the very elite class of people into research and development, right? Then a lot of universities are going to get built. A lot of professors, researchers, people who are going to put it out in the work, they're going to get employed. And whatever we have in the classical world, people are going to question that, and they're going to make it more robust. So whichever way you look at this, one of the biggest advantage, even if all this is not going to work, is that all of that wealth will be created, all of the new people will be employed, and we would have made our existing processes more robust and actually challenge them in the light of quantum advantage. How can that be a bad thing? Another way to just look at this.
Not quite the research question I was looking for, but okay.
Yeah, I know.
Helen, I'm going to have to bail as well, I'm afraid. It's 11:15 at night here, but I'd like to thank you and the audience and all the questions, and Anna, and let's keep this conversation going. Thank you.
Thank you, Eamon.
Thank you.
Thank you.
Thank you all then.
Thank you.
Mhm.
Thank you very much.